Hello, welcome to this video. In this video, let us compare Otto, diesel and dual cycle for same compression ratio and for same heat rejection. Now, let us start with PV and TS diagram so that we can compare. So, let us start with PV and TS diagram. Pressure versus volume, temperature versus entropy. Okay, let us start with Otto cycle. Now, Otto cycle comprises of reversible adiabatic compression, from 1 to 2. Then 2 to 3 is constant volume heat addition. Okay. 2 to 3 is constant volume heat addition. This is reversible adiabatic. P for gamma is equal to constant. This is volume constant. Okay. Then we have again reversible adiabatic expansion from 3 to 4. 3 to must go parallel to this line. Now, this is 3 to 4 and then we will have 4 to 1 constant volume heat rejection. 4 to 1 is constant volume heat rejection. So, this PV power gamma is equal to constant, this is volume constant. Similarly, we can draw it in TS plot. So, 1 to 2 is reversible adiabatic compression. So, this is our 1 to 2. Okay. So, 1 to 2 is entropy constant or reversible adiabatic compression. This is entropy constant. Then 2 to 3 is constant volume heat addition. So, constant volume would look like this. Constant volume heat addition. So, we can also write here, this is our QS for Otto cycle. Okay. This is our constant volume. Then 3 to 4 again is isentropic expansion. Okay. So, 3 to 4 is isentropic expansion. Then 4 to 1 is again constant volume heat rejection. Constant volume heat rejection. Now, this is simple because we are just drawing one cycle. Now, let us add, on the same plot, we should write diesel cycle as well as dual cycle. All right. Let us start with dual cycle. Now, for same compression ratio, that means compression ratio is represented by V1 and V2. So, for same compression ratio, we can say that this has to be maintained same. So, we cannot go to the right or to the left. So, compression ratio same means this volume V1 and V2 should be same for the diesel cycle and dual cycle. At the same time, this 4 to 1 represents heat rejection. You see, this 4 to 1 represents heat rejection, or in TS diagram, this plot 4 to 1 represents heat rejection. So, this has to be also kept same because we are talking about heat rejection is also same. Now, let us write 1, 2, 3, 4, 1 is representing Otto cycle. Okay. And we are saying that since we are talking about heat rejection is represented by 4 to 1 and this is common for all. Okay. So, heat rejection is represented by 4 to 1. So, in particularly Otto cycle, particularly Otto cycle. We can talk about heat supplied, that we will talk little later. Now, let us take dual cycle. Now, what is dual cycle? Keeping the same compression ratio, let us start from 1 to 2. Then after heat addition, partial heat addition is happening at 2 2, let us call this as 2 dash, 2 dash. Then we will have heat addition at constant pressure. Now, we will have to stop at this point. We will have to stop at this point because heat rejection has to be same. In order to keep the heat rejection same, if you go like this, then again reversible adiabatic comes like this, because then heat rejection becomes more than that, or you cannot stop even behind also like this point. So, then this has to go in parallel with reversible adiabatic expansion, because you cannot have this line which is not parallel to this. So, we will have to be stopping exactly at this point. Okay. In order to keep the heat rejection same, 2 dash to 3 dash represents heat addition at constant pressure for a dual cycle. Now, in order to keep the heat rejection same, it has to be stopped on this line. Then again this will be 3 dash to 4 dash, then 4 to 1. So, that means now we have got a cycle 1, 2, 2 dash, 3 dash, 4 and 1 is our dual cycle. Okay. Now, similarly here, let us go for 1 to 2 is okay. Then 2 to 2 dash, somewhere here we will have to take constant pressure process, 3 dash. Now, this is our constant pressure process. Okay. Now, heat rejection is remaining same. See, 4 to 1 has to be same. So, that is what we are trying to maintain. If you go towards right or left, this heat rejection changes. So, we are not changing the heat rejections, therefore, it has to meet at this point only. Now, therefore, heat supplied will be different for these cycles, because heat supplied is represented by what? 2 to 3 represents heat supplied in Otto cycle, 2, 2 dash, 3 dash represents heat supplied in dual cycle. We can write that as well. So, we can say or we can extend this line, just for the sake of measuring heat addition. Okay. Let us call this as 5 and 6. If you check here, this much area, all right, this much area is heat supplied in Otto cycle. So, we can write area 5, 2, 3, 6, 5, 5 to 3, 6, 5, or we can also say it like, it is actually area under the curve in a TS diagram represents heat, right? Area under 2 to 3, that is nothing but area 5 to 3, 6, 5 is heat added or heat supplied, let us say QS. This is for Otto cycle, all right. Similarly, for dual cycle, what we can write? For dual cycle, area under 2, 2 dash and 3 dash is the amount of heat supply. That means area 5, 2, 2 dash, 3 dash, then 6 to 5. Now, this is what is heat supplied in our dual cycle. Okay. Now, let us go for diesel cycle. Now, diesel cycle is 1 to 2 is same because we are keeping same compression ratio. Then 2 to 3, I mean it has to be a constant pressure heat addition. Okay. For constant pressure heat addition, let us go like this. And we know that in order to keep same compression ratio, it has to be stopped here. All right. Now, this is 3 double dash. Okay. So, here also we will have to go like constant pressure line. Now, this is 3 double dash. Same compression ratio, same heat rejection. Now let us say 1, 2, 3 double dash, 4, 1 is diesel cycle. So, heat rejection is same, but we can measure heat supplied. Now, area under in a TS diagram, of course, we are talking, these are all in TS diagram. In TS diagram, area under 2 to 3 double dash represents heat supplied, or we can say 5 to 3 double dash 4, 6 and 5. This area is so I will just erase this. Okay. Now, area under this curve represents is heat supplied in diesel cycle. Now, we can compare which one will give us more efficiency. Now, let us compare it. Now, what is an efficiency equation? Efficiency is given by heat, W by Qs. W is Qs minus Qr by Qs, or we can say 1 minus Qr by Qs. Okay. Now, just check this. This numerator is same, all right. QR is same. So, we will not worry about QR. For all the cycles, auto, diesel and dual, QR is same. So, for the same QR and same compression ratio, this is varying, QS is varying. Now, let us check what will happen to the QS value. Now, if this term is 0.1, this will be 0.9, that is 90%. If the second term is 0.2, so this will be 80%, all right. So, if you concentrate on the second term, we are subtracting it by 1. So, if the second term is 0, you will have 100% efficiency, then that is not possible, but what we are trying to say is that second term has to be minimum in order to get higher efficiency. Now, in order to get minimum, second term to be lesser, what option do we have? Either in order to get the second term lesser, we have to have QR should be less, okay, numerator should be less, then we will have the second term less, or QS should be greater, high. Okay. So, QR should be less or QS should be high. So, what we can conclude is heat rejection is being common, we can say for same QR, we can say for same QR, if QS is higher, efficiency is higher. Therefore, we can conclude which QS is higher. Now, we can see Otto cycle has highest heat supplied for the same heat rejection. So, because that area is 5 to 3, 6, all right. So, we will start with this. Now, area 52365 is greater than area 522-3-65 is greater than area that is 523-465. Now that means heat supplied in Otto is greater than heat supplied in dual, greater than heat supplied in this cell, which means efficiency of Otto is greater than dual, greater than efficiency of dual. Now that is what we wanted. For same compression ratio and same heat rejection, efficiency of Otto cycle will be higher than dual and it will be greater than efficiency of diesel cycle. Thank you.